recording now, you should have heard right now Zoom letting you know that it's being recorded. We ask that you follow the general webinar courtesy rules, that you keep your microphone muted if you're not speaking, and the presenters will give you the floor as needed. This is particularly for the Q&A session, where we invite you to either put your questions on the chat or to directly ask the questions to the speakers. As the last point mentions, you can enter your questions for the presenter on the chat. Otherwise, again, you can ask them directly. Now, next slide. Perfect. So this is just to give you a bit of a taste of what's coming in this webinar series. So as I said, today we're starting with drought impact assessment. But as I said, this is just the first edition in a series of 5 webinars that will take place throughout the winter. So the next topic will be biomass and carbon fluxes in December, then followed by agriculture and crop calendars in January, followed by biodiversity in February, and then urban green in March. You can sign up for all of these webinars on the same registration site where you signed up for the drought impact assessment webinar. Maybe you have actually already signed up for the other webinars. If that's so, you will receive more information about each one of these webinars as we get closer to the date, when we will share with you more information and the link to join us. And now I give the floor to Ludvig for an introduction and overview on the product.
Thank you very much, Sophia. As Sophia introduced me, I'm Ludvig Forslund. I'm working here at the European Environment Agency in Copenhagen within the Copernicus land monitoring team, where I'm managing the high-resolution vegetation phenology and productivity product, which is what we're looking into here today. This product is providing a systematic monitoring throughout the EA38 area plus UK. So that's our general area of interest where we produce products for. And it's monitoring the state and evolution of the land surface in a general sense. It can be found under our biogeophysical parameters product family, where you can further look into the vegetation part of it and find the HR-VPP presented in 3 different categories or product levels. I will get into that a bit later. So let's start with what is phenology and productivity. So as a general definition, the phenology is the timing and development of the photosynthetically active leaf foliage. It's visible as stages of leaf development. So, for example, the bud setting, leaf growth, and leaf shedding. And it relates to the internal plant processes, which are affected by external factors, which are, of course, light, temperature, and water. And then productivity is the accumulation of vegetation biomass. It's denoting the plant growth in general, and is often measured in gross or net primary productivity, and is mainly affected by vegetation vigor and health. So the HR-VPP product suite, just to walk through the processing stages of it and how it's delivered to users. We're starting off, of course, it's mainly or purely based on a Sentinel-2 time series from 2017. It's using the level 1C product from ESA, where we are then performing the atmospheric correction within the production using the Centicore the core processor. And from this, we produce daily near real-time processing of 4 vegetation indices that has been selected. These being the NDVI, the FAPAR, fraction of absorbed photosynthetically active radiation, the leaf area index, LAI, and the plant phenology index, PPI. And for the rest of the, and we can show it like this exactly. For the rest of the production, we then use only the PPI. So the 3 other vegetation indices are purely processed and delivered to users in a near real-time manner. So then we take the PPI and construct this, what we call the seasonal trajectories, by applying a function fitting and gap filling of the time series of PPI data. And from here, from these seasonal trajectories, we can then produce the annual phenology and productivity metrics or parameters by extracting the different metrics from the function of PPI. And both seasonal trajectories and the VPP parameters are produced yearly, but the seasonal trajectories are delivered in a 10 daily time series, while the metrics or parameters are delivered are produced annually. And here I want to just introduce you briefly to the reference data used. So HR-VPP is using a large number of reference data sets, both for the initial calibration of the production phase, but also for the product validation on an annual basis. And here we are using GPP measurements from eddy covariance flux towers. We're using phenological cameras for extracting the greenness on kind of near remote sensing. We're also using the PEP 725, which is the manual field observations of phenology. And further, we're using using agricultural crop data from Belgium and Austria to calibrate and validate the product. And the visualization of the vegetation indices. So as I said, we mainly use the PPI, and here I just invite you to what we did as an initial assessment of the vegetation indices input, and why PPI was selected, which is clearly visible here, as it's the most sensitive for highlighting the phenological stages of the main land cover types. But as I said, all of these can be retrieved from the products. And further, to visualize the seasonal trajectories, here we see the function fitting. We see the raw vegetation indices, that's black points, and the function that we clamp towards as the green dashed line, and the 10 daily data as seasonal trajectories, the yellow dots. So this is to create this smooth time series and gap fill, so we have a value every 10 days for every pixel throughout the area of interest that we use. And from this, as I said, we can then extract the phenological stages. Here, just 3 of them are highlighted as the start of season, the peak of season, and the end of season, as the green triangles there. Then to highlight the power of the high resolution that is the HR-VPP, which is then enables distinguishing between the seasonality between, for example, here different crop fields, and also what is visible here is, of course, the drought that affected the southern Sweden in 2018, which is clearly visible as a disruption when the time series reaches July, where you have a sudden drop of PPI values. We can wait for July. Here we see it clearly. I don't know how well this this GIF works on over the presentation, but I hope you see it well. And then finally, the phenological metrics or the parameters here visualized for a tile. So we have 13 of them, and also for many, both the date, for example, the start and end and peak of season, both the date and value is recorded. Then from there we can record the length, the slope of the green up and the green down, etc. To the bottom left, you see a representation of the parameters and the function that we use, and of course we see here how we derive the productivity metrics as the integral of the function. So for each season, this is done. Image to the bottom right shows productivity statistics aggregated on per land cover. So just as an example of how the data can be used as a first stage. Further, just another example of assessments we can be used to, for example, study the influence of altitude on start of season using a transect up a slope. And of course, it can be clearly seen how the season and the starts differently depending on the elevation. Here, this example is from a valley in Austria. Then HR-VPP is also well documented with detailed descriptions. We have the product user manual, which goes through many of the important details to be able to access the data set thematically speaking. We also provide the algorithm theoretical basis document to give the full detail on how the product is processed. Also, further the validation methodology and results are presented in the validation reports. We have produced one for the base time series, the 17 to 20, and then we update with the yearly updates we perform. Then there's also descriptions on how to access the data. There's many different ways of accessing the data. It's a cloud hosted data set. So there's both the human-based access and also machine-to-machine APIs, etc. to utilize. And also we provide a number of scripts for access and also doing quick assessments like a pixel time series assessment tool and so on. The HR-VPP is also currently undergoing a bit of evolution. We, of course, foresee to continue this production. It's a valuable product for many downstream applications. We intend to increase or to move it into more of an above ground biomass estimations, introducing GPP, potentially NPP estimations as well in the productivity metrics. And this might change how we process the overall product in terms of seasonal trajectories and VPP metrics, etc. We also foresee that we will do a reprocessing to align with the Sentinel-2 Collection 1. The Sentinel-2 throughout this year has underwent a full reprocessing of the archive, and we want to align with the improvements that have been introduced there. Further, we also foresee that probably there will be quite a alteration to the near real-time vegetation indices that have been produced within the product in the past. We foresee that these will be reduced and streamlined towards more what is used within the VPP product. So that was the first part of the webinar, introducing the product. I will now hand over to Lars, who will describe the use case. I will stop sharing. Who will describe the use case of drought impact assessments. And that this webinar is about. Are you able to? Yeah, here it comes. All right.
Hey, thank you, Ludvig. So my name is Lars Eklundh. I'm from Lund University, and I have been working with the product development and also been engaged in a small study that we made on drought effects. So my presentation is called HR-VPP for studying vegetation impact of the 2018 drought in Europe. So what is drought? Well, we can probably all agree that it's a prolonged period of low precipitation leading to water shortage. What is important to notice is that droughts evolve gradually. they seldom have a very well-defined start, and sometimes not a well-defined end either. We can estimate drought with an index called SPEI. There are also other indices, but this is a very common one. And this index considers the balance between precipitation and atmospheric evaporative demand. So basically how dry the climatological drought conditions is described by this index. So we also know that droughts may lead to very severe effects on the ecosystems, but also on the societies at large. But most probably we are all aware of the strong effects on the agricultural production. And what we also know is that drought is probably being amplified by climate change. So we may see more of droughts in the coming years. So we have a map here of the aridity conditions of Europe. And what we can conclude is that basically south of 45 degrees north latitude, we have a negative water balance. So those areas are, of course, very, very sensitive when we discuss drought. But also further north, there may be concerns regarding drought. So we made very recently a study across Europe where we looked at the drought sensitivity in a longer time perspective. So we used 20 years of data and an ensemble of different vegetation indicators. And we saw that response to drought varies geographically across Europe, and that is not so strange, of course. We also saw that the autumn is showing the strongest vegetation response to drought. And we can see that in the map below here, that we have a very strong effect, particularly in southern parts of Europe, but also across Central Europe, and especially focused on the autumn period. Also, the summer period is vegetation response to drought conditions, not as strongly as the autumn, but still. Whereas in spring, it looks quite different. So actually, the spring vegetation growth seems almost to be negatively related to drought conditions. A warm period a warm and dry period could actually be beneficial for the vegetation growth. So this was a European study, but within HR-VPP, we focused more on the sort of local scale effects. So we looked particularly at the 2018 drought in Northern Europe. And of course, as you know, this was an exceptionally dry year. It was very warm in the spring, and then we had a dry summer. We saw very strong effects on crop yields. For example, in Sweden, we had the lowest crop yield since 1959. There were many forest fires, and also we noted, particularly in Sweden, an increase in bark beetle populations. So the use case here was to investigate the use of HR-VPP for local drought-related effects on the vegetation. We looked at these 6 study areas across Northern Europe, and when we summarized the SPEI drought index for these areas, we see that 2018 really stands out as a very dry year in comparison to the other years. So let's just talk a little bit more about the different time perspectives on the drought. If we look at this drought index from 2017 to 2018, we can see to 2020, we can see that 2018 really stands out as a very dry year. We have strong negative index values of the SPEI. Now, this is in a short time perspective, so we have used 3 months to aggregate the data. If we instead aggregate data over 1 year, so 12 months, we see a totally different pattern. And here, 2018 doesn't stand out as a very dry year, but instead the drought is focused on 2019. So there is this lag effect of drought that is very important to realize. And also the fact that it's not strictly defined in time, but it's sort of, it has a certain dynamic and a certain evolution that is important to realize. So now over to the case study. So we are focusing here on southern Sweden. So this is an area dominated by agriculture, and we have several of the most commonly used or most common species or crop types in Europe, like spring barley, rye, autumn wheat, autumn rapeseed, sugar beet, hay fields, and so on. We analyzed HR-VPP data for each one of the crop fields of the area of interest. So we knew exactly what was growing in the different years on these crop fields, and we could analyze the HR-VPP data for each of the fields. We saw also in the crop statistics that 2018 was a year with very low average annual crop yield in comparison to the other years. So this is a 20-year time series, and 2018 clearly stands out. So we can look at some individual time series for different crops. Here we have the different crop types, and we have the colored lines are those from HR-VPP data, and the black line is that from the drought index, the SPI. And we can see that in 2018, the SPI really was very low and with a strong negative deviation. But we also see that for most of these crops, there was a very low index value from HR-VPP. So the satellite observed much less vegetation productivity during the year 2018 in comparison to the other years that were normally much higher. And this pattern seems to be recurrent for the different crop types around this area. So we can summarize this information in a graph. We summarize across all the crop fields. And here in this top graph, we see the total productivity as measured by the satellite and the HR-VPP product. And we see that 2018 was strongly negative in comparison to the other years. And this pattern actually mirrors quite well what we see from the crop yield statistics. So this is from the Swedish Central Bureau of Statistics. And we see that crop by crop, we have exactly the same pattern in the crop yield deviation. So this gives us very strong confidence in the HR-VPP product. We see that on average, we can actually see what is going on during these extreme events. We can also focus in on individual croplands or local areas and recognize sort of the crop fields. We have, of course, a patchwork of different crop types in such an area, but overall, we saw a very strong deviation in 2018. So the PPI, the plant phenology index, was very much lower in that year in comparison to the other years. So we also looked at forests, and here are examples from statistics for forest areas for the 6 different areas in Europe, and they have these different colors in the bars. And we have the amplitude, so this is the height of the seasonal curve, and we have the total productivity, which is the integral of the curve. So these two indicators, when we aggregate them across different forest areas, we see that actually 2018 doesn't stand out that much, neither for the amplitude nor for the total productivity. But what we see is that in 2019, we seem to have a more negative response. So both for the total productivity and the amplitude, not so much response in 2018, but 2019 stands out. And this is especially obvious when you look at deciduous forest species. So here we see a quite clear pattern that 2019 was had a negative deviation in comparison to the other years. So how does this work? Well, we can again remember the SPI, the drought index. We had the short-term drought index that was very negative in 2018 and not so negative in 2019. But the longer-term SPI index was more negative in 2019. So I think this explains the response of the tree vegetation, the forests, that are more sort of affected by long-term drought, and the agriculture is more related to the short-term drought. So here we are zooming in on a local forest and grassland area. We have a forest here, some grassland, and an urban area. And we can see that in 2018, this forest area actually had slightly positive values of total productivity from satellite, whereas the grasslands were strongly negative during that year. The grass areas were totally brown or yellow most of the summer. But in the next year, it's looking different. We have slightly negative values of productivity in the forest, and in the grassland, it's more neutral, I say, some positive and some negative areas. So this again displays this difference between the grassland, the open land areas, and the forest areas. So this takes me to the conclusions. Drought effects on vegetation can be monitored with HR-VPP data. The HR-VPP parameters total productivity and amplitude are those that show the strongest responses to drought. We also looked at most of the other vegetation parameters, but they don't seem to have responded that much during the drought. The local drought patterns are clearly visible across croplands and grasslands, but there was no decrease in forest productivity during the drought year, rather a small increase in the productivity. We did, however, have a decrease in the forest productivity on the year after the drought. So I would conclude by saying that the relationships between drought and vegetation are very complex, and they are modulated by a number of different factors, for example, the vegetation type, the climate zone, etc. And I think that HR-VPP has such high resolution spatially, but also a good time resolution, that it can help us to elucidate and investigate these patterns and these effects much further. So I will stop with that.
Thank you very much, Lars.
By the way, I should acknowledge my co-workers, Zhanzhang and Hongqiao Jin, who have participated in the development of this study.
Exactly. Thank you very much. Very interesting. And to remind you as well, all of these webinars are based on a white paper that has been published on the CLMS portal as well. And the three upcoming, or the three webinars, the first of this series are already published, and then we have the upcoming that will be published at the beginning of 2024. So if you want to read more into details as well, then the white paper is available for your read. Okay, so now I want to give the floor to Eva Ivits, my colleague here at the European Environment Agency, working very much into the drought impact assessments, etc., where she now will, using these type of data sets, the phenology and productivity data sets, where she now will give a presentation on exactly drought impact monitoring, and also what they have constructed as a spatial temporal data cube for Earth observation data assessments. Yeah, please go ahead, Eva. We see we don't see it in full screen presentation mode.
Now?
No. Oh, we did when we tested earlier. Maybe it's just slow.
Mm-hmm. I can try to send it again, share it again. It seems.
Yeah, we see your screen at least, but yeah, maybe it's stuck.
Can you hear me?
Yep.
I can see the presentation on screen in presentation mode. I'm gonna try to share it again.
Yep.
Let's see now.
Yay, there we go.
All right.
Perfect. Thanks.
For the glitch, I don't know what happened. So welcome everyone. Good afternoon. I will now give a bit different presentation than what Lars showed. I will try to explain how we use HR-VPP and similar time series products for supporting European policy making, which is our core business here at the European Environment Agency. This presentation is shared with Maxime Lamar from Synergize Shared Planet /Planet. Maxime will explain this and he introduces himself. We need people like Maxime and companies and researchers in Europe to help us in our work in our small agency. And Maxime was very influential in the work we have developed here. So you should be now seeing the next slide. Yes. So how do we monitor drought and their impacts for policy support? Lars has presented a bit already what drought is. I will now pick out details what makes it very important for policy making. It is a recurring natural hazard, and the very important thing is that it can occur anywhere in Europe. So as the animation shows, the red colors indicate certain drought impacted areas in the year between 2000 and 2019. Indeed, it does occur everywhere. It even occurs in the Boreal region and in the Nordic regions. So therefore, we have to monitor it everywhere in a continental scale if we want to support European policy making. Drought is a lack of precipitation, but the way we monitor it is that we need to compare it to an average normal condition to know that, yes, indeed, in a certain year, we had a drought impacted area. This is very important because that means that we need long time series, which has initiated us to search for partners like Maxime, who enabled us to work with lots of data, what a long time series means. That is also very important because it propagates through the water cycle. So it results in low soil moisture and soil moisture deficit. It's vegetation, water stress, low flows in lakes, reservoirs, low groundwater levels. So it really is a very complex phenomenon, as Lars has suggested, but also it has lots of related impacts. For example, it does contribute to the destruction of wildlife habitats, to increased stress on endangered species, to loss of wetlands. It does contribute to increased number of wildfires, which are again very detrimental in Europe, and we see more and more wildfires occurring in areas which have not seen wildfires before. Dry soils are prone to wind and water erosion. A drought also induces loss of harvest, poor soil quality. It impacts biodiversity and ecosystem services, and it also can lead to loss of carbon sequestration or decrease in carbon sequestration, as well as direct CO2 emission in case of very low groundwater levels, so when we have aerobic condition in the soils. So all in all, it also leads to land degradation, and because of all these issues, there is a very high policy demand at the moment, well, not at the moment, but lately, on monitoring the impact of droughts, but also to keep very frequent updates, annual updates, which are transparent, repeatable, and understandable for policymakers. Now, to do that, we at the agency are facing some challenges. First of all, as I said, impacts occur on a continental to global scale. So we need to have to support the EU and the European Commission on a continental-wide analytics where we had a drought. We need observation over large spatial scale, spatial extent, Hence, we need to use data which cover entire Europe as a wall-to-wall coverage, all ecosystems, so every grid cells, every pixels. Because it is a recurring event, we need observation with a high repeat frequency. At the moment, we are looking into annual data, but from next year on, we need to look into decadal data, so meaning every 10 days, because we need to be able to observe how ecosystems recover after drought or do not recover. So we are there already that we need large-scale, continental-scale data. We need to monitor the entire continent with very high repeating frequency, but also in order to be able to counteract the impact of droughts, we need to identify management needs and options, and for that, we need very high spatial resolution. And last but not least, as I said in the previous slides, that in order to define that a certain ecosystem on a continental scale is under drought being an extreme event, we need to be able to say that this event is extreme, is an outlier, is different from the long-term normal condition, and hence we need long-term observations. And this for an agency as us, and I guess to many scientists out there, is a big challenge. Because let me repeat, we need to have continental extent observations, we need high temporal frequency, we need high spatial resolution to identify impacts and identify land management options to counteract impacts, as well as long-term observations. And this is a huge challenge. We also, because of this, we also have some challenges with the processing. I am making here a mistake, which I always say I will not make, to present something on a slide which you can't read. But I still wanted to put this flowchart here, indeed not to read, but just for you to understand that every single box in this flowchart is a processing step. Let it be some kind of ML algorithm or machine learning algorithm or some just zonal aggregation of results, writing out images, writing out tables. Hence, a processing of all these images by itself is also a challenge. Also because we need to test our assumptions, we need to adjust thresholds. Hence, one needs to rerun analytical processes when one wants to address a continental scale assessment of droughts. Then we want to explore results. We need to be able to plot charts and images. Sometimes only just part of the workflow needs to be reiterated. And of course, then there is also the question, where are my data? Where did I save it, etc., etc. So not only we have lots of challenges in drought, and specifically in an agency like us, who are not researchers, but address using research results for policy making, because it's a very complex topic with lots of processing needs. Now we have some solution to these challenges. For example, for the challenge that impacts occur on a continental and global scale, but land management needs to be implemented locally and need to be implemented, and so that land management options needs to be implemented. Luckily, we have the Copernicus Land Monitoring Service, high resolution vegetation, phenology and productivity portfolio. I will not go into the technical details because Ludvig has introduced the service very well. But we also need to be able to combine all these images with other Copernicus Land Monitoring Service data to know in which ecosystem we are, in which land cover we are, is it a protected area or not, is it floodplain or not, but also with external data like LPIS data, which would give us like plots, agricultural plots or forest stands. So not only the HR-VPP data is huge, but we need to be able to combine it with something else. And also I'd like to mention that we don't bring the data to the user anymore. That's one of the big data paradigm, but we need to be able to bring the user, so us, to the data. Yet again, another challenge, because this huge amount of data sets and the flexibility the processing requires means that the data need to be processed where it is stored. But then again, we have, as I said, there were other challenges, like, for example, deviation from long-term normal conditions, which means that the comparably low or a short time series of HR-VPP, because it starts in 2017 onwards, needs to be combined with long-term time series. For example, the soil moisture index from the JRC operated Copernicus Emergency Monitoring Service dataset, as well as the medium resolution vegetation phenology and productivity dataset, which is on 500 meter spatial resolution, and it is also Copernicus Land Monitoring Service data. So with all this, I wanted to exemplify that a continental scale analytics of local impact is really not a business as usual scale. It is still huge. I guess I can say that also for Copernicus service providers, for big companies out there, is still not something that can be solved easily. But luckily, we have companies and people like Maxim who I have managed to group with and collaborate with this project. And now, Maxim, I would give the slides over to you for your part to illustrate how we have implemented the processing all these data in a spatial temporal data cube. Do I need to stop sharing the slides, Maxim? Or can you share yours?
Okay. Do you see mine now? If I switch backwards, forwards here?
No, I think Eva has to stop sharing first.
I did.
Now it updated for me. Sorry.
Okay, I'll just do that.
Exactly. Yeah, so I
Right.
can just introduce Maxim. Eva briefly introduced. Maxim is working for the European Topic Center, and as Eva said, is helping with hands-on data assessment. Please, Maxim.
Yeah, thank you, Ludvig. So yeah, just a quick word about me. I wear many hats. I'm currently working at Planet, which is, as probably most of you know, a commercial satellite data provider. But today I'm wearing the hat of Synergize. And Synergize is a European company whose mission is to drive Earth observation users towards new ways of working with data and moving towards the future of data processing in the EO world. And you probably know us better for our products called Sentinel Hub. We also have a strong involvement in putting the word out to the community about data cubes and how these can leverage the data that you're processing. And I think this example today is a great piece of work where you see the collaboration between domain experts like Eva and us technical companies who can bring the tools to help these visions come to life. So I'm just going to run you quickly through the way we implemented all that theory that Eva has been talking about and how we got from this idea with this complicated chart you saw to actual products. So our developments started from two main points, technical challenges, which, as Eva mentioned, are that the impacts occur at continental scale but manifest locally, and deviation from normal conditions need long time observations, which means that we need to observe phenomena at a large extent with high spatial resolution over long time series, and this means a lot of data. We were driven by a certain number of requirements. This isn't your typical, I'm a scientist processing on my servers or my local computer and then producing data for a paper, but we really wanted the results to be easily explorable online so that people don't have to have expert knowledge to be able to browse the data, so that it's accessible to a larger number of publics. That these data needed to work hand in hand with the systems that EEA have in place. So we wanted the results produced by the algorithms to be ingestible in analytics dashboards. And also that you could derive statistics from these results, because this is really where you're getting the value out of the information. There's no point in producing pixels if you can't transform that into actionable information. And lastly, we wanted something that was very flexible because as you probably all know, the HR-VPP product suite isn't a static product, right? It's updated. Some variables are updated on a daily basis and all the way up to yearly for other variables. But we need to be able to take that in account and update the outputs of our algorithms on a regular basis. So this is an exercise that has been done for a while now at EEA with the medium resolution vegetation products. So these are products which are 500 meters and they cover the last 2 decades. The idea here was to work hand in hand to be able to derive some indicators and added value information, but using the HR-VPP, so at 10 meters resolution. So there's a big step there from one to another. Now, why is there a big step? Well, because when you're working at high spatial resolution with a lot of products, you're churning through a lot of data. And so all the attempts to do this in a traditional way, so either on computers or even servers locally, failed more or less. So we had to think of innovative ways of how technology could support the processing of such a large data set. And we were very lucky because this data is hosted on Wikio. So Wikio is one of the dioceses, which means that the data is hosted in a cloud optimized format, online accessible, which means that these data sets are compatible with cloud services such as the Eurodata Cube. So you'll tell me, what is a Eurodata Cube? Well, Eurodata Cube is an initiative that was funded by ESA, whose goal was to drive forward this kind of analytics. So you can picture it as a sort of a layered cake, if you like, with the bottom layer being the data lakes. So Eurodata Cube sits on a whole bunch of different data sources. These can be open data or commercial data that are streamed through different cloud providers. And the tools that are within the Eurodata Cube allow us to tap directly into the data streamed by these cloud providers and work with data in the cloud and on the fly. And you have a certain number of processing services there within the Eurodata Cube, such as processing services, Jupyter Labs, cloud compute environments, and also services that make your life easier. Now, I'd like to point out that that was a year ago, or a little over a year ago, and the landscape, EO landscape in Europe is evolving. Eurodata Cube is coming to an end this year and is being replaced by the Copernicus data space ecosystem, which is now the main access point to European EO data. So if you haven't heard of it, I'd recommend you check it out. You can access data, you can access services, and everything that was in the Eurodata Cube is now in the Copernicus data space ecosystem. Okay, so back to our processing. So we had a whole bunch of different data sets. So HR-VPP was one of them, but we also had to combine the inputs with other types of data, ranging from very different spatial and temporal resolutions. And all this was churned into our algorithm. So the way we did this, very naively, we started with IVA to find a very easy processing pipeline and thought, this is great, we're going to finish this very quickly. And we started with small data cubes to test over a specific region. Of course, you know all that science doesn't work this way, and it was an iterative process, and we were discovering things along the way. And so through trial and error, we got rid of this very easy pipeline and came up with this chart here, which is not meant to be read, but just to show you the complexity of what we were doing here. Once we had this in place, we were able to then run these pipelines, test it over a data cube in a specific area of interest. Once we were happy with that, we didn't suddenly start processing at 10 meters over Europe. You need defined steps when you work with such big data sets. So what we did is that we did a first run at the continental scale, but at very low resolution to get an idea and to learn how things work, what doesn't work, how we can improve the algorithm. And then, only then, once we were happy with these results, we were able to go up to higher resolution and produce the full data sets at 10 meters. To give you a few numbers, we processed almost 1 terabyte of data. The processing was parallelized in the cloud, split over 500 virtual machines, and it amounted to about 50,000 processing hours. And we were pushing the services on Wikio really hard because we were hitting those buckets and those data sources with tens of thousands of requests per second. We thought we would break it. Surprisingly, it held up pretty well, and we were able to run in a couple of days the whole process. And just a note about the budget, a run like this algorithm would cost around 10 to 15,000 euros, which may sound a lot like that, but when you look at the amount of data you're processing and the results you're getting, this is relatively cheap compared to if you had to split that processing through traditional methods. So here's an example, a couple of examples of the output products. Here we have some soil moisture anomalies computed over Europe. If you zoom in, you can go to a country level. So here we have some information about growing seasons over Spain, and then you can go all the way down to the parcel and get information like, for example, this map here, which is the total drought impact, where basically you're looking at the total productivity where you have drought. So you can really go from this massive overview of the continent all the way down to the local impacts. So the lessons learned from this exercise, I think it's a good idea to share the lessons and the challenges learned, is that having the data on a DS like Wikio is really a huge advantage for modern day processing because you have that easy access to data. You can explore the data and then you can process the data yourself, which will drive innovation, drive derived products from these data sources. Using cloud-based services like the Eurodata Cube or Copernicus Data Space ecosystem, you have all the sandboxing capabilities, which means you don't have to download a whole bunch of data, you don't have to duplicate it, you can test your algorithms on small areas and then scale up step by step. Talking about scalability, when you move to the cloud with such systems, you're not limited anymore in the volume of data processed. Apart from then it just becomes a matter of cost. And you can flexibly run this algorithm for updates. So we were able to do that when new layers of HR-VPP were coming out. And finally, you have interoperability because your data is in the cloud, so you can either stream your data to through front-end platforms or directly to dashboards for policymaking. And you can offer these results to the community without them in turn having to download petabytes of data. However, this way of working doesn't come out without its set of challenges. A couple of these are that you have to think very differently, right, when you're processing in this way. It's not anymore this trial and error that you're running locally. You have to think of ways of optimizing your processes. The processes take a long time at such a scale, so you have to test and implement slightly differently than how you would do traditionally. And what we learned is that where the data was available, we had the tools to process it. I think we can do much better in terms of integration with platforms, cloud platforms. Not all the data sources that we needed were available. And this is really something that we need to keep getting the word out there that when institutions like EEA or like Copernicus initiatives produce data, it's very important that they're made available openly on the cloud. And finally, of course, it was crunching a lot of data. So you have to think, does this make sense for me? Is the value that I'm producing with this data worth the cost of data storage and processing? And with these technical considerations, I'm going to pass the word back over to Eva.
Yes, thank you, Maxime. So I just have 2 more slides just to round it up. Thank you, Maxime. So yes, we have done the work. We also have published now an indicator on the EAS website. The link can be accessed at the end of this presentation to be able to bring the right messages to the right user. So, for example, in many cases, policymakers are interested in one message, what has happened in Europe. So, with all the statistics and time series and analytics, we can say that indeed the last decade, so the most intense drought events, and the area impacted increased continuously. I have actually, Maxime, this is another slide. I had another message here, but maybe I can just say it, although it's not written on the slide, that we have also seen that 2022, in 2022, Europe experienced the hottest summer and the second warmest year on record, and our indicator indeed shows that the drought impacted area was largest in 2022, around 630,000 square kilometer, as opposed to the 167,000 square kilometer average between 2000 and 2022. So here we would need to update the slides here, Maxime, because the data goes till 2022, but we will correct it. Yes, indeed, we can give the detailed message to policymakers. We can go down now to country level. We can say that croplands were most impacted in Portugal. Forest productivity decline was the highest in Sweden. Grasslands were most affected in Austria. And we can also now address the very detailed message, which tells us or enables us to explore on the continental level which agricultural plot in which country was most impacted and where do we need support most with proper land management or financial means. Next, please, Maxime. So future potential, this collaboration between us, the EE, knowing what policymakers need, what is the message we need to bring out there, and the collaboration between the scientific communities showing us methods to observe the impact of droughts, and people like Maxime and the companies who can show us how to do it on a large scale. It really empowers us, the EA and others, to do these steps alone in the future. It is a very spatial temporal data cubes are very flexible to ingest new data sets, which we will need because all the time, because new data comes up and there's a new policy question to answer. So we need to be able to ingest new data. Dissemination of the results become easier in dashboards. For example, such dashboards and results disseminated in web platforms is a place for policymakers, academia, and industry to work together. And with this, all this information gathered together, derived from Earth observation data, the huge data we have, into very simple messages like in a dashboard, it really does facilitate policies like nature restoration investments. And with this, we are actually addressing or approaching near real time and near real detail analytics of drought impacts, which leads us somewhere in the near future to digital twins. But that's another topic, I guess, another seminar. And last but not least, yes, this is our last slide. If you would like to explore the indicator and the dashboard, You can find them under the first two links on the European Environment Agency's webpage, and on Eurodata Cube on the Copernicus Data Space Ecosystems. The Copernicus Data Space Ecosystem. There are links here put by Maxim. And I guess, Ludvig, the slides will be distributed so that users can have a look. Okay.
Exactly. Thank you very much, Eva and Maxim. Very interesting indeed. And yes, we will distribute the slides. This recording will also be made available for users who couldn't, or participants who couldn't participate. Sorry, we are running a bit over time. This webinar was intended for 1 hour, but of course we don't want to skip the questions and answers from the participants. There's no in the chat as of yet, but please, if you want to post a question, please do it in the chat. We can bring it up, or turn on your camera and microphone, and yeah, if you have a question to any of the experts that have been presenting today.
You can also, on the reactions button, you can raise your hand if you want as well.
True. While you might maybe think about questions, I highly recommend go and check the results that Eva and Maxim are producing. There's many interesting dashboards to explore these assessments that are being done, and reports that are supplied into the policy context of Europe, specifically here on droughts. Seems there are no particular questions.
I think everything has been very clear, and we don't have any raised hands.
I could just suggest perhaps that our emails will be distributed, so if participants have questions after the seminar, they can always contact us.
Exactly. And please explore the data sets on the CLMS portal. They are also available on Wikio, and as Maxim introduced as well, the data space ecosystem. And don't hesitate to contact either the experts here today, or contact the CLMS help desk for if you have any questions or clarifications. And also the manuals I briefly mentioned, to understand better what the data sets include. And finally, don't forget to register. You register for this one. Maybe you've already registered for the rest of the webinars, but there's some very interesting topics coming up, as we explained in the beginning, on agriculture. Biomass estimations is the next one, and biodiversity, and then applications for urban green, to use HR-VPP for all of them. So please register for the ones coming up. And with that, I want to say thank you, and see you next time.